Okay. So a student of mine asked me a question about the how does coefficient of thermal expansion works with the energy separation curve. So I just want to explain that from the beginning, which is let's talk about the atomic basis for Young's modulus and coefficient of thermal expansion, as well as other properties such as bonding energy and so on. But let's just focus on these two. And let's start from an ionic bonding model. In an ionic bonding, you have a cation, say positive there, and an anion, which is a bit bigger, just drawing it, exaggerating it. But the distance from its nuclei center is, let's call that R, which is the separation distance, right? And if you think about the energy, the potential energy versus R, that's called the potential energy, the U. Okay. And let's define positive as being repulsive, and negative as being attractive. Then you'll see two components of this energy separation curve. The first component is attractive, and you'll be familiar with a form of this law. It's called the Coulomb's law. Coulomb's law. So Coulomb's law says that the energy Coulombic, as a function of R, is equal to some sort of constant. It's actually Q1, charge 1, charge 2, divided by 4 pi permissivity constant of vacuum times R. And then R is to the power of 1 for ionic, right? In this example here. So let's just call this, because one of the charges is negative, so it'll be attractive, a constant A divided by R. Yeah. So that's the attractive. So if you draw this UR curve, you'll see something like this. As the R is very far, then it's very small, close to 0, and as the R is very small, the energy is very large. So you'll see something like this. Yep, sorry, it doesn't cross the 0 line. Excuse me, I just clean that up a bit. Excuse me. This is x-axis there in terms of R. This is the Coulombic energy separation curve. But as the R gets closer and closer together, the R gets smaller, then the electron clouds of the cation will mix with the electron clouds of the anion, and then suddenly there'll be repulsiveness going on, and from the clouds, and it'll start somewhere close, and it'll sort of jump up very quickly, like this. Okay, so that's the energy repulsive, and as you can see, it's quite steep. So the energy repulsive here, is a positive number, some sort of constant, be divided by R to the power of n. Let's call it, okay. Where you can n is what they call Born exponent, and it's usually somewhere around 9 to 12. So very big compared to R to the power of 1 for ionic, right? So when you add them up together, U to the power of R, sorry, U as a function of R, there are two components to it. One is minus the attractive component, A divided by R to the M, where M is equal to 1 for ionic, and sort of 4 to 6 for covalent. So that's the attractive term, right? And then you have the repulsive term, B to the power of R to the power of N, which is the, I said between 9 to 12. That's the repulsive term, okay? And the easiest way for me to explain this in terms of other types of functions as a function of R. Let's start with U first, which we've drawn before, right? So it looks something like this. Not very nice, sorry. So it's fatter over here and very steep on the left-hand side. So let's just clean that up a bit. Excuse me. Yep, so that looks better. So it looks like this, okay? And I present to you that there's two other curves. And this one, let's call it F, force, and this one is Young's modulus. And this where the energy is minimum there. Let's call that R as the equilibrium R of R naught. Okay, R naught, R naught here, R naught. Okay, I'll present to you that F and U is related as follows. Most of you from high school know that energy or work, energy or work is equal to force times distance, right? Force times distance. So U is equal to Fr, where U is in joules and F is in Newton and R is in meters. Yeah. So du dr is actually F. Yep. So F is actually the first derivative of the top curve. And what about Young's modulus? Well, we know that stress is equal to Young's modulus times strain. Sorry, times strain. And strain can be thought of as proportional to R, which is the distance. The bigger the R, the bigger the strain. And well, sigma is proportional to F, right? It's F divided by A. So I'll present to you that dF, dF dr is proportional to Young's modulus, which is the slope. Oh, sorry. Yep. So Young's modulus is actually the second derivative of the du dr curve. I should write that as proportional. So let's draw the F curve now from this. So the slope of the the energy separation curve is 0. The slope is 0, right? At R naught. So it crosses the Fr crosses R naught there at 0, x-intercept. And then on the left-hand side of that R naught, you can see that the slope is very negative initially and then reaches 0. So it's very negative, reaches 0. And then on the right-hand side of R naught, the slope is positive, 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 but declining to 0, but never reaching 0, asymptotic. So positive, 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 but declining towards 0. So it looks something like this, but never reaching it. Okay. Sorry about that. Du dr is equal to F there. And then the slope at R naught, Fr, is actually pretty constant. And that's why we have a positive number, yeah, of maybe slightly declining with increasing R, of a positive number of Young's modulus. That's why you have a Young's modulus for aluminium, for iron, and so on, it's positive number. So that's the basis for Young's modulus from this model. So that hopefully you can see the three relationships here: the first derivative, second derivative, right? Okay, what about coefficient of thermal expansion, which is the question from our student that I started in the first place. So the situation here, the energy separation curve, the minimum number that happens at temperature, let's call it T naught, of 0 Kelvin. At higher temperatures than 0 Kelvin, then let's use a different color. Then the cation and anion in this example jiggles more, right? Jiggles more, than the R naught generally increases backwards and forwards, goes backwards and forwards, oscillating left and right, and sort of goes like this at T1, where T1 is bigger than T naught. And at a higher temperature, it sort of does this at T2. Because it's not symmetrical, the right-hand side is more than the left-hand side, right? And then at T3, something like this. And so on, oscillating, and T4, and so on and so forth. T4, something like this. Where T4 is bigger than T3, bigger than T2, bigger than T1, bigger than 0 Kelvin. And the average of these two locations, for example, this oscillation at T1 here from left and right here, is somewhere here, right? And the average at T2 from the right hand side to the left hand side is somewhere here. The average of T3 is somewhere here. At T4 is somewhere here. Therefore, it goes, with increasing temperature. Sorry, I'm not drawing this right, but the R naught, the equilibrium separation distance, interatomic distance, increases with temperature. So the R naught at T4 is bigger than the R naught at T3 and so on. So that's the basis of a coefficient of thermal expansion. So increasing temperature increases the interatomic distance of the whole material, metals or ceramic or polymers and so on. So hopefully that makes sense to you. Why is that? Because of the non-symmetric nature of the energy separation curve that we explained before. It's sort of fatter on the right-hand side and very steep on the left-hand side. So the average is kind of moving to the right. You can see that very clearly as the temperature goes up. So hopefully that explains that clearly. And I want to thank you for listening.